Hello everyone! Welcome and thank you for attending this talk in this unusual format. My name is Julien Garteau. You may know me in the demo scene as Zavie of Control Test and Tokyo Demo Fest. And today I wanted to share with you some of the new things I've learned recently about light and physically based shading. We're first going to see how light interacts with matter from a physics point of view with as much detail as we can given the time we have. Then how some shading models try to reproduce the effects of that interaction for rendering purposes. And finally, I'll briefly talk about a work-in-progress implementation that we're doing for our demo engine. There is a lot of material to cover, so I'm going to try to go fast. The slides together with the text of this talk will be available online. Now, my goal is to improve the rendering of our demo engine, support more diverse materials with a richer, more complex, more interesting looks. When implementing a shader, I want to understand what I'm doing, I want to understand what's going on, why a shading model does certain things. I want to develop an intuition of how things should be so that if things go wrong or if there is doubt, I want to be able to reason about it and find my way toward a solution rather than just being stuck in the dark. Unfortunately, this is a fairly deep rabbit hole to explore because to understand the shading, you need to understand the model underneath. To understand the models, you need to understand the physics of the interaction of light with matter. And the more you dig, the more questions start popping out here and there. Why this? Why that? And before you know it, you're knee-deep reading stuff about quantum mechanics. I am really still very much in it. There are many things, many areas that I still don't understand, but I thought I could already share with you some of the things I've learned so far. All I will be presenting today is my ongoing understanding. It is quite possible and likely even that there are mistakes. When there are parts I've noticed I don't quite understand yet, I will try to mention it, but I recommend you take all of this with a grain of salt and do your own research. Let's start with light. There is a thing called the electromagnetic field, and that field behaves according to the Maxwell's equation, which describes it entirely. And this video of 3 blue 1 brown does a really good job at giving you an intuitive understanding of what those equations mean. Waves propagating through that electromagnetic field are called electromagnetic radiation. Light is an electromagnetic radiation. More precisely, visible light is a slice of the electromagnetic spectrum from 400 to 800 nanometers, give or take. So you can imagine that as waves traveling through space, just like sound waves do, for example, and the distance between one wave and the next one is 400 to 800 nanometers. So how much is that? If we convert to micrometers, that's 0.4 to 0.8 micrometers. And to put things in perspective, a single thread of spider silk is, like the ones you see over here, is about 1 to 8 micrometers. Another point of reference would be cigarette paper, which is about 30 micrometers thick. So the wavelength of light is very small, but not to the point of being beyond our imagination. And if we look at an even smaller scale, this radiation is made of photons. You can see photons as tiny bits of pure energy. They have a wavelength as well. The higher their energy, the shorter their wavelengths. But they are said to be quantums of energy because they are indivisible. Like you cannot take a photon and split it in half, for example. These elementary particles, they don't have mass, and they travel through the vacuum at the highest speed known in the universe, which is the speed of light. There are experiments that show photons behave like a wave, for example, the double slit experiment, which gives you this interference pattern, and we know this pattern is not caused by having like many photons. We can reproduce it with a single photon. Yet, there are also experiments that show photons behave like particles, like the photoelectric effect, which was first explained by Einstein, earning him his Nobel Prize. If you haven't heard of those experiments, look it up, it's really cool. But so, photons are both waves and particles. When a photon meets another particle, many different things can happen. There is the Rayleigh scattering, the Mie scattering, the Compton scattering, the Thomson scattering, the Rayman scattering, just to name a few. The more energy a photon has, the more mayhem it causes. But I'm only going to talk about a certain kind of interaction between a photon and an atom. Atoms, like you know, are the little bricks of matter. They are made of a nucleus with a proton and a neutron. Well, sorry, protons and neutrons, sorry, and electrons orbiting that nucleus. Like photons, and if I understand correctly, like all elemental particles, electrons behave both like particles and waves. So despite the typical popular image we have of the atom, electrons don't orbit the nucleus with clean orbits like planets do. Instead, they form an electron cloud with a sort of wavy shape in which they have a probability of being, which is what is represented over here. Those electrons, they can be at different discrete energy levels, and each of those energy levels correspond to a different orbit, from the ground state to higher and higher energy state until they have enough energy to free themselves from the atom. Let's use a simpler representation for a second. Each orbit over here is an energy level. To move up from one state to another, the electron needs exactly the difference of energy between the two levels. And likewise, when moving down, the electron will release exactly the difference of energy. So when a photon meets an atom, the question is whether the atom has an electron that could use exactly that amount of energy to move to a higher state. If there is no such electron, the photon doesn't interact with the atom and continues on its way. If there is such an electron, the photon is absorbed and the electron goes to that higher state of energy, and it is said to be excited. Then, after an extremely brief moment, the electron will eventually get back to its lower state of energy, and when that happens, a new photon is emitted with exactly the same amount of energy. Also, because this interaction was so brief, the atom didn't have any other interaction, so conservation of momentum causes the emitted photon to also go in the same direction as the original one. So it's as if the photon stopped at the atom for a very brief moment before continuing on its way without any change. Now, if you imagine a material with many such atoms, and photons going through that material and stopping at each and every atom they meet, you can see they would progress more slowly than in a complete vacuum, and so you can see why the speed of light is slower in that material. Before I continue, I too will pause for a moment to mention that, as far as I understand, this is just a simplified model. For one thing, a photon doesn't interact with one but with an infinity of atoms at the same time, and it's a superposition of those interactions that gives the result. Also, I've read a different explanation about how a photon being a perturbation of the electromagnetic field and the atom being a dipole, it's more correct to say that the photon causes the atom to oscillate, which in turn causes a new perturbation of the electromagnetic field and thus emitting a new wave. And this is happening with all the atoms in superposition. Anyway, like I said, it's a rabbit hole. Regardless, light travels at a slower speed in the material. And a consequence of that is when you have a wave traveling at a certain speed, if it enters a material and now propagates at a different speed, it also changes direction. I have a shader that demonstrates just that. So here is a shader on Shader Toy. This shader doesn't know anything about direction of waves, except for the original source of the wave. All it cares about is the speed of the wave and maintaining the interface, like the boundary condition, where one wave, two different waves are at the same position. And just by changing the speed of the wave inside the material, it changes direction. So let me show you with a different speed. So here we have a wave going twice as fast as outside of the material. If we change that to the same speed, there is no change of direction anymore. If we put, if I recall correct, the difference of speed in water is 1.33. We have a change of direction that is the same as in water. Okay. So, where were we? As you probably know, This effect is called the refraction. The ratio between the light of speed in a vacuum and the speed inside a material is called the index of refraction of that material. If you derive Maxwell's equation at the interface between the two materials, you can obtain the Snell's law, which gives you the direction of the refracted light. Now, having talked about refraction, the question that comes after is, what about reflection? When photons arrive at the surface of a material, there is a chance that instead of entering that material and being refracted, as we've seen, they get reflected. They don't really bounce off the surface like a ball on a wall. They do get absorbed by the atoms at the surface just like before, but this time, instead of being re-emitted in the same direction, they go in the reflected direction. Unfortunately, I haven't found a clear explanation yet of why that happens and why that happens to some photons, but not all of them. Maybe it has to do with the mechanical properties of the atom structure that will return the momentum in that direction. Maybe it is that photons are sort of emitted in all directions at the same time, and the interference between the wave just adds up destructively except in those two directions, and then a photon randomly goes in one or the other. I don't know yet. It's just another gallery of that rabbit hole to explore. Let me show you another shader. I believe you're all familiar with this pattern that we've all seen many times in old school demos. If you give me just one more second. Okay, so yeah, we have two emitters here that are interfering with each other. And we're going to change the number of emitters. We're going to increase it. And look at what happens when I increase the number of emitters. So right now we have 2, and now we make it 4, and we make it 8, and then 16, 32, and now you should start seeing something happen. The pattern is quite changing right now. It doesn't look like the same anymore. Actually, now we don't even have a pattern anymore. We just have like sort of a front wave. I'm going to put a big number, like over 1,000 or something like that. And now we have like a really clean wave. And this is actually the shader I was showing to you before. It's exactly the same, just with like many emitters along the interface, and that's all. And they're just interfering with each other. And now we can change the waves inside the material like we did before. So we have the refraction that happens, and we can also show the reflected wave like so. Let me show you full screen for a second. So you might say, well, this is not really interesting, like it's just a flat plane. So we can try to make it more interesting by adding like some bumps and so on to the surface. And then this is how it starts looking. And again, there is no idea of the direction of waves or anything. There are just like many emitters along the interface that are interfering with each other. And I think it's super cool that we get this effect with just that. Like now you can really see, for example, if I put the incoming wave like this, you can really see the rays of light that start forming. So you have a ray of light bouncing off the surface over here, then you have another one that bounces off over here, and you have another one bouncing off over here. And at the same time, you have rays of light being refracted in different directions. And this shader doesn't know anything about rays of light. All it knows about are like small emitters that are interfering with each other. And you can even see like how over here you have like some diffraction that happens, but that diffraction gets distracted by other waves, and you only get like this ray over here. So I think it's really cool that we can get an effect like that with just that. Up. Okay, so let's get back to our slides. Up. So, if we derive Maxwell's equation at the interface using the boundary conditions, we get the Fresnel's equations. And those equations, they tell us how much light is either reflected or refracted depending on the indices of refraction, the wavelengths, and also the polarization of light, which is why we have those two equations here, but I'm not even going to touch that topic. In these equations, the index of refraction is a complex number because it also accounts for absorption, which we will see right now. So back to our atom. When it is excited after absorbing a photon, something else can also happen. If the atom is part of a molecule or a lattice, for example, it might transmit its energy and momentum to other absorbers around it. That would depend on factors like the mechanical properties of the molecule or the amount of energy. This is an area I haven't studied yet, so my understanding of it is extremely limited, and on top of that, it's apparently also something really complicated. But if we imagine our material again with many such atoms and photons going through that material, and some of them with certain wavelengths getting absorbed never to be seen again because their energy is dissipated into the structure, you can see how the more distant those photons go through that material, the fewer of them remain with those wavelengths in particular. And what we've just described right now is absorption. This is what you see when you look through tinted glass. Not that the metals have a structure that makes them very good at transmitting energy, so they tend to have a very high absorption. Like photons that enter metals are gone after a distance that is super short. So far, we've imagined the material made of the same stuff, but with no irregularities whatsoever. That's the case for gases, for water, for glass, but the majority of materials in real life are not like that. Instead, they are made of all sorts of microscopic cracks and gaps and irregularities, different indices of refraction, like all sorts of things stuck together. If we imagine again all these photons going through this, very soon they will hit one of those changes of index of refraction, and when that happens, as we've seen earlier, they will change direction. And soon after they will hit another change and change direction again, and again, and again. And there is a point where that will have happened so many times that you can consider the direction of those photons to be now completely random. What we've described here is scattering, and it's the reason why instead of being transparent, snow and milk, for example, are white and opaque. If we imagine that on top of this scattering, photons with certain wavelengths also get absorbed never to be seen again, like we've described earlier, we get light that gets tinted before coming out of the material in random directions, and scattering plus absorption is what explains the color of most objects around us. There are other really interesting effects that can happen. Can you try to guess what's going on over here? We have a green laser beam, then it becomes red, and then it becomes blue. It's not absorption, because green laser doesn't contain red wavelengths, and it doesn't contain blue either. So what gives? On the left side, atoms receive photons that make them jump not just one, but several energy levels at the same time. And when those electrons fall back, they do so in several steps, each time emitting a new photon of lower energy. The sum is the same as the original one, but they have lower energy. And lower energy means longer wavelengths, and that's why the beam becomes red. And on the right side, it's the exact opposite effect. Atoms absorb several photons in a row, and then release the whole thing at once, emitting photons of higher energy level, and therefore shorter wavelengths. This effect is called fluorescence, and that's what happens with black light, which is UV, which is invisible to the human eye, makes materials glow when you are at a party, unlike now. So let's recap and see how we can model all of this. We have waves of light traveling through a medium. Actually, no, let's simplify that already. We have rays of light traveling in a medium. And when they reach the surface, some of them will get reflected, and we call that the specular reflection. For most material, there is little reflection, like just a few %, and it's mostly independent from the wavelengths, so the color of the reflected light is the same color as the incoming light. For metals, however, the reflection is strong, like typically above 50%, and it may depend on the wavelength, so it can get noticeably tinted, and that's why that's what explains gold and copper, for example, which have like strong colors. The rays that are not reflected are refracted, and just like we saw, most materials cause refracted rays to scatter and get absorbed. So when they eventually get out of the material, the rays are tinted and go in random directions. Here, scale matters. If before getting out, rays tend to travel a distance that is so short that at our scale it looks like it's zero, we call that the diffuse reflection. And as we've seen earlier, metals absorb refracted rays immediately, so the diffuse color of metals is black. If that distance is long enough that we notice, we call this subsurface scattering. That's what you see when you see light through your hand, for example. But they're physically the same, we just model them differently. Now, why mention scale? Here is another random microphotography image I found on the NASA website. It's some material, it doesn't matter. What's important is the amount of detail. There are cracks and irregularities everywhere, and the whole thing is probably too small to see with the naked eye. So we probably don't need and don't want to simulate all of that. But those details are still going to matter when it comes to how the material looks. It means that our surface is not really like this, but more like this. Yet at our scale we don't see any of that, we only see the result. So we see something like this, basically. And if we're trying to reproduce the appearance of such a material, for example, if we are looking from here, what we want to know is how many of those rays are reaching us. And clearly, the number of rays is going to depend on where we are. Like, we're going to have a different number of rays if we are over here. So for a given viewing direction, we want to know how much rays we're seeing, so that we could. So what we could do is look in every direction and count the rays we get. And if we try to represent that, we would obtain something like this, maybe. And this blob over here represents the distribution of rays for all directions. This would tell us for any direction what we'd get. What we've done here is move from a simulation to a probability-based model. And that's super important because now we don't need to know the details anymore. We just need a good distribution function that's consistent with the details. A function that would depend on the direction of light and the direction of the viewer, and that tells us how much light is reflected, is called a BRDF, Bidirectional Reflectance Distribution Function. And now, the entire game is to find a good BRDF. One very popular model is the Microfacet model, and the idea is that if we consider the microscopic surface to be made of tiny, perfectly flat surfaces, for the specular reflection, for example, the only microfacets that we care about are the ones that will reflect the ray in our direction. The other ones are going to reflect the rays in other directions, so we can just ignore them. And we know which facets they are. They're the ones with this normal vector, which is halfway between the light direction and the view direction, so we call it the halfway vector, h. And now we need a function that tells us the proportion of microfacets that are aligned this way. That's called a normal distribution function, and it's usually written D in shading models. This distribution is going to depend on the geometry of the surface. If it's more smooth, for example, the rays will tend to be reflected in the same direction. If it's more rough, they will tend to be reflected in more different directions. So what we can do is represent that with a parameter which we call the roughness, and it's often noted alpha. There are many classic NDF. There is Phong, Blink-Phong, Beckman, Gaussian, but nowadays pretty much everyone uses GGX. We saw earlier that only a part of the light is reflected and the rest is refracted. So to take that into account, we could use a Fresnel function, usually noted F. Very often people use the Schlick approximation, which works well for non-metals, but be careful though, because for metals, it does miss some of the feature of the response. Now you say, hold on, that doesn't work. Like, this ray over here doesn't reach the eye, and this ray over there doesn't reach the microsurface in the first place. So we need to take that occlusion into account. That's the role of the geometry function, usually noted G. Again, there are many available, but apparently Eric Heitz proved in 2014 that Smith was the correct geometry function to use. And now you may say, hold on, again. If we have the same amount of light arriving in this direction, or rays in this direction, it's not the same thing. Like the energy is spread over a different surface. So we have to take this difference into account. And we have to take it into account twice, once for the light direction and once for the viewer direction. So finally, if we put all the pieces together, we get the Cook-Torrance model, and that's a BRDF very popular for the specular reflection. We haven't covered the diffuse reflection yet, but I ran out of time and it's even more complex than the specular, so maybe next time. So, I've mentioned that for each Lego brick, we have many options available, so how do we choose them? To answer that question, I propose we look at a few selected works. The first reference I want to mention is the MERL database. They measured actual BRDF of 100 materials, and they published the data. So it's a super important reference from 2006. With that, you can compare your own model with actual measured data. There are a few visualizer out there. Patapom wrote one a few years ago. 2012, what everybody now calls the Disney BRDF, they looked closely at the MERL database and compared it to existing models, and they noted which models were good or not on like things the artist cared about, especially the diffuse at grazing angles, and then they decided a number of parameters that they wanted to have. They put the bricks together and they defined their own empirical shading model to mimic the behavior they observed. They designed it to be robust and expressive, but also simple and intuitive for artists. It is a milestone in PBR literature. Nowadays, most modern shading models, at least, are partly based on this. The next year comes the paper about the shading model in UE4. It's strongly inspired by Disney BRDF, but also much simpler. The Disney people, they cared a lot about the diffuse BRDF, but in UE4 they just went for a Lambert diffuse. The reason they give is the cost of the function, and to them the look was not different enough to justify that cost. They also explained that it was problematic for spherical harmonics. And that is a very important point. When choosing a shading model, it has to work everywhere. Like if you have point lights and area lights, it should work with both. And if you have environment mapping or light baking, it should work there too. So if it doesn't, you will have like inconsistencies. The course note of the UE4 paper also mentioned that a lot of work was done to compare various available bricks, and the author, Brian Carris, lists them on his blog. So that's also important. You can look there if you want to try and choose between different functions. For image-based lighting, they introduced the famous split sum approximation, which we can, with the result over here. That's for environment mapping, which uses one big integral, and this approximation allows to split the integral in two parts. One part is convolved, and the other part is baked into this lookup table texture. So when you see a shadow that uses a texture that is red and green like this one, that's the split sum. Then comes Sébastien Lagarde in 2014 and his work on Frostbite, the engine used by EA. This one is a fantastic reference because it explores many aspects of PBR, not only the materials, but also the light sources, the light probes, the camera. It is very thorough. The course notes are over 100 pages long. Like UE4, the shading model they propose is strongly inspired by Disney. They actually keep the Disney diffuse and they even improve it. It is an excellent read for anyone serious about PBR. And finally, there is Filament, the rendering engine made by Google. The documentation of Filament presents the shading model used, the choices they made, the alternatives they had. The quality of the document is outstanding. It's a complete introduction to PBR, and it seems to become a reference for PBR implementations. That's all I'm going to present for now. Otherwise, I would still be here talking about this for an entire day. I'll mention though that last December, I've put together a long list of good references organized by topic with summaries. There is a lot of reading there, so if you're looking for PBR material, check it out. And now, a very quick demo of what we have. Here are my goals. I want to be able, well, here's my, I should say, like my Christmas wish list. I want to be able to compare and choose between different models like they did. But I don't want to be stuck to stay stuck with one shading model and have everything look more or less the same. I want to be able to change my mind. I want to be able to switch between shading models from one demo to the other. And I want to do that in the context of size coding for 64K or even 4K, for example. Now, don't get too excited. What I'm going to show is a very early prototype. So there is nothing like groundbreaking over here. It's more about like throwing ideas and seeing what works. And I hope that maybe you two will have feedbacks and ideas to share. Okay, so if you give me just a second. I'm going to launch the demo. Well, actually, no, I'm going to yes, the demo. Where is my demo? It is over here. So this is our internal ad hoc tool to try to experiment with things. And this here is a little prop that was in our last demo, probe. It looks a little bit different from the demo because the demo was using image-based lighting, and here we just have 5-point lights. But this is the shading we were using at the time. So this is like a blind phone with Fresnel put together, half broken, but I was still happy with the look. And here is our work in progress. So we have this visualization of the so this is like a playground, a test ground, a sandbox, if you want, of the shader we're doing. The first row is ray traced. The second row is rasterized with a forward rendering, and the third row is rasterized with deferred rendering. And you can see it has like a low mesh resolution, so that if there are like glitches and stuff like that, I really want them to be really visible. The last row has to do with the Disney paper. So let me show you that for a second. Hop. Here is the Disney paper from 2012, and I think it was paid. So they have this representation here of different BRDF, and they explain it on page 4. Because a BRDF has like too many dimensions to be easy to represent. So they did some work on how to visualize a BRDF, and one thing that they mentioned is this slice of the BRDF, although it's incomplete because it's just a slice, gives a lot of information about the stuff that the artists care about. And then they compare their own shader, like they visualize their own shader and compare it to the to what they have in the MERL database. Here it is. So this is the shading model that they wrote and how it looks with that representation. So this is what we have here, and you can see it's really quite different. It doesn't look really interesting, and that's because what we have here is blind phone with a Lambert. So let's change that a little bit, and before doing that, I'm going to show to you how this works. Okay, so this here is our main shader for the prototype. It's not very interesting per se. It's mostly boilerplate. But what is interesting, one thing to mention is we have this hack over here where we have this keyword include that we introduced, and when we compile the shader, it basically copy-pastes another shader into the shader we're compiling. So what's interesting is this shader over here. This is my to-do list, basically. Like over here, I have like all the functions I've seen from different papers and things like that. So it's the stuff I want to test and compare. And the first part is stuff I haven't tested. And after that comes the stuff that I've already tested and that I've put together. So here, for example, you have the Schlick approximation of Fresnel for monochromatic based on F0. Then you have the same function for like RGB. You have another Schlick Fresnel, but this time with the index of refraction as a parameter. Then you have the normal distribution functions like Beckman, Blinfong, Gaussian, etc., etc. Then we have the BRDF. So here, for example, is a Disney Diffuse BRDF, the one from the paper. And the more we go, the more we have like top level things. So at the end of the file, we have the actual BRDF. So FD for the diffuse and FS for the specular. And the way this works, so you see like there is a lot of boilerplate, a lot of macros. We have those macros at the beginning of the shader, and the goal is to pass them from the compiler. When we compile the shader, we want to pass those parameters, and they will enable or disable certain features. So for example, if I put the demo again, over here, I can switch from, say, I can switch from the Blinfong to the GGX, and now it looks a lot more interesting. You can see that now the so you can see that now the white reflection, like the specular reflection, looks a lot closer to what Disney has. And if we enable the Disney diffuse, so we replace the Lambert over here with the Disney diffuse, we get this. So we have like on the left we have like this darkening, and on the right we have this red spike, which you can see over here. So how this is done and why? So this is my shader again. So we have those macros, and again the goal is to pass them from outside. We try as much as possible to have the same notation for all the functions. This here I said is stuff that I haven't tested yet. So let's go to the stuff that is production ready, so to speak. So those macros are going to enable or disable the functions, because I don't want all this big shader to end up in my 64K, but I want to keep those functions because I want to be able to choose one and then choose another one. So those macros are going to enable that function. And then this function here is going to require certain parameters. For example, the Schlick is going to need the v.h parameter. So here, when this is enabled, it's going to enable the compute vh. And later on, when we go at the bottom, here we have a data structure with all the common parameters that we need for the different functions. And what was it? The v.h is over here. So when the macro is enabled, this is going to appear. And then when the macro is enabled, this is going to get computed. And finally, we have the top level shader, so like the diffuse function, for example, with like all the things appearing together. So the goal here is that by choosing the parameters we have, it's going to generate the shader with all we need, but only what we need. And so that way, the shader is going to be like the smallest amount of code for the shader we want. After that, the shader minifier will do its job and make this even smaller. So I can show you a little bit like some differences between the shader. Nope, that's not what I wanted to show. Okay, so over here. So this is our visualization. Maybe I can show back the this guy over here. So this is the shader that was used in the demo, although it was image-based lighting, and here it's just 5 lights. I can switch that to just 1 light. Okay, so here is how it looks with one light. And sorry, let me fix that. I made a mistake. Nope, that's not what I want to do. Okay, so here is how it was looking in the demo, except for the image-based lighting. Here is how it looks with 1 single point light, and you can see it's not really looking good. Like, even though here it's okay, here it's really not good. And now, if we switch the specular for GGX, we get this, which is a lot better. It doesn't match it anymore, because like the roughness for one function doesn't necessarily match the roughness for another function. So it's a little bit difficult to have those functions really compare at the same level, but still. And now, one question is about the diffuse BRDF, because, for example, UE4 was, like, the paper of UE4 was arguing that it was not really worth the trouble having something different than Lambert. So here, this is Lambert, and I'm going to enable the Disney diffuse, and you can see the difference. So it does look different, like you can see something change, right? Let me put it again. This is Lambert, it's boring. This is Disney diffuse, and see how you have like this reflection at the edge, like it's really bringing you back more red color. Lambert again. Disney again. So this is what I had to show for you. I hope you found this clear and useful. I'm sorry I couldn't go into more details. Like there is a lot more that I wanted to talk about, but I just didn't have time. Maybe there will be a part 2, I don't know yet. This over here is the link to the slides. And I guess I will be seeing you in a moment on the seminar voice chat for any question you might have. And I will be staying on the Demoscene Discord server anyway, so feel free to get in touch. With that, it is time for me to wish you have a great party, everyone. Stay safe, stay healthy, stay home, and make beautiful demos.